what is a back titration? So titrations you probably know from GCSE, or when you take an acid and you react it with an alkali, and the purpose of it is to find out how much of one of those is needed to react with the other. You might just want to know what volume is needed, or you might be trying to find an unknown concentration. So you may know the concentration of the acid and you want to find out the concentration of the alkali, and by doing a titration you can find out exactly how much of each are needed to neutralize each other, and then you can use a moles ratio from the chemical equation to work out the concentration of one if we know the concentration of the other. So the difference between that and a back titration is when you're doing the titration on the leftovers from an experiment. So for example, you react an acid with maybe a carbonate, which is solid. The acid is in excess, so all of the carbonate reacts and then there's some acid left over. So we then do the titration on the acid, which is a normal titration that we react with the alkali. We do the titration in the normal way, we do the calculation in the normal way to find out how much acid we had. But the purpose of it is to find out how much of the original thing we reacted. So if we were reacting it with a carbonate, we're doing the titration on the leftover acid from the original reaction in order to find out what we had in the original reaction. So hopefully this is going to be make a bit more sense if we look at an example. So just going to look at briefly at an example of a back titration question. We may not go through the whole thing, but hopefully this will help you to understand what's going on and how to work out what you need to work out. So I'll just change my camera angle. So this is a question from an AQA AS level paper, and it's telling us that we've got a reaction of calcium compounds and we've got a pure solid that we think is calcium hydroxide. The solid can be identified from its relative formula mass. So ultimately in this question we want to actually find the relative formula mass of this calcium hydroxide, or of this solid, in order to ascertain whether it really is calcium hydroxide or not. The relative formula mass can be determined experimentally by reacting a measured mass of the pure solid with an excess of hydrochloric acid. Okay, so this is the key that I mentioned. We have an excess of hydrochloric acid reacting with the solid. And this is the equation for that reaction. So we have, this is what we're trying to find out, and we know that we have an excess of this acid. So the unreacted acid, so what was left over, is then determined by titration with standard sodium hydroxide solution. So I'm going to just do that in a different colour. I like using the different colours just to kind of help identify what information we have about what different reagents are in this. So we're provided with 50 centimetres cubed of 0.2 mole per decimetre cubed hydrochloric acid. And it wants you to outline, giving brief practical details, how you would conduct an experiment to calculate accurately the relative formula mass of the solid using this method. So this is an interesting question because it doesn't actually give you all the information that you would need to actually do the calculation. This is an 8-mark question that's actually focusing just as much on how you do the practical as doing the calculation. So the first thing, as I said with back titrations, the first thing to really appreciate is the fact that the titration is happening on the unreacted or leftover acid that's left over from this. So the first mark that you get in this question is to work out how much acid, or how many moles of acid you want to make sure you, or how many moles of the calcium hydroxide you want to actually react with the acid. So the only thing we know in this question is the amount of acid. We have the volume and concentration of the acid. So we can work out the moles of the acid by doing, by doing volume in decimeters cubed, so divided by 1,000, times by concentration. So that's going to be 50 over 1,000 times by 0.2, and that will give us the moles of the acid that we actually had at the beginning. Okay, so I'm just going to do that on my calculator. So 50 divided by 1,000 times by 0.2 is 0.01. Okay, so this is how many moles of acid that we have to work with. So the first thing about appreciating that we need an excess of acid is identifying how much of this calcium hydroxide we should react with that. So in order to have an excess of this acid, we want to make sure that we have less than 0.01 moles of calcium hydroxide, or that pure solid, which is what we're interested in. So if we, actually I say that 0.1, actually looking at this equation, we've got a 1 to 2 ratio, which means we need less than half of this amount. So it's actually less than 0.005 moles, because if we had any more than 0.05 moles of calcium hydroxide, then we're going to use up all of the acid, and we need to make sure that there's an excess that will allow us to titrate. So we can write that in moles, but it might be useful in this question we're trying to explain how we're going to actually do this experiment. Might be useful to actually calculate the mass then. So the mass of CaOH2, we have to calculate from the moles and the MR. So the moles and the MRs, moles times MR. So that's 0.005 times the MR of calcium hydroxide, which is, I believe, 74.1, will give us the mass, the maximum mass that we can use of that solid. So this is the kind of thing that you'd be expected in an 8-mark question to discuss how much mass of solid we're going to react with this volume and concentration of hydrochloric acid. And then based on how much we had, we would expect a certain amount of acid to be left over. But we may not know how much that is because we don't know for sure if this is a pure calcium hydroxide. So then we do the titration, and we want to measure out the acid using a pipette and add the weighed amount of solid into the conical flask. We titrate the leftover acid with our sodium hydroxide, and if we're not given the details, we might want to say what concentration of the sodium hydroxide are we going to use. And perhaps what volume. We normally use a standard volume of 25 centimeters cubed in a conical flask measured out with a pipette. Make sure you say that you're going to add the indicator, for example. I can just see someone ask a question, how do you know when there is leftover acid? It's not a silly question at all. So if we look at the molar ratio for here, there's going to be leftover acid if there's more moles of acid put into this reaction than calcium hydroxide. And because of the moles ratio, we need twice as many moles of hydrochloric acid. So in this case, we had 0.01 moles of hydrochloric acid, which means we need half as much of the calcium hydroxide in order to fully react with that. And because we want some leftover, we want to make sure we're using less than this number of moles of calcium hydroxide to make sure that there is going to be a leftover. And in this situation, we don't know exactly how much will be left over, and that's why we're doing the titration, to work out exactly how much is going to be left over. So we're going to say what concentration of sodium hydroxide we're going to use, and then that will give us a volume and concentration of the hydrochloric acid that was left over, which will allow us to calculate the moles of the acid that was left over. And from the moles of acid that was left over, we can work out how much must have reacted, because we know we had this much to start with. If we work out the moles left over, then the moles reacted will be this, let's call that 1, minus this, let's call that 2, and that will give us 3, which is the moles reacted in that first equation. And then from that we can work out the moles of the calcium hydroxide we have, and from that we can work out the MR, because we know what mass we put into the equation at the beginning. So hopefully that makes a little bit of sense. I know that back titrations are quite complicated, but the key thing to remember is that we're titrating the leftover from another reaction, and it's kind of that link between the titration and the other reaction is what can often be hard.